Hey, embedded developers. Remember last time you were debugging your device with some proprietary tool, hard to use, complex, didn't have all the features you needed? This time is over. Pier-Yves was in your situation and decided that it'd be good to have an open source tool doing all of that. It's called Scrutiny Debugger, and Pier-Yves is on the IoT Show to tell us everything you need to know about it. The client-server architecture, how it's not intrusive, how you can do real-time debugging, and so forth. If you like the show, do not forget to subscribe, tell about it to your friends, get notified for the next episodes, give us a like, leave a comment. Thanks for watching. Hey everyone, this one, as I mentioned earlier, is for embedded developer. We'll talk about debugging, testing, visualization of your C and C++ code. And for that, we have Pier-Yves, who has developed a very interesting open source tool. Pier-Yves, how are you?
Hi, Olivier. I'm fine. How are you?
Okay, Don, I described everything, right? What we're going to talk about?
A little bit more to say about it.
Okay, there you go. Awesome. So before we get into that, and we point people to the fantastic GitHub repo and explain why they should care about your open source tool and start contributing and using it, how about you tell us about yourself? Who is Pier-Yves? What are you doing in life? And, where are you calling from? Things like that.
Okay. I'm a software engineer, embedded software engineer based in Montreal. I have a background in electrical engineering. And I've been working in embedded system for about 15 years. I have a background in automotive in the automotive industry. I've worked as a control algorithm engineer for electric motors. So I've been designing control algorithm for power converters, so embedded chargers, motor controller, those type of product. And I am now working in embedded AI as of today.
Okay, aren't we all, right? And as a matter of fact, I'm always laughing a lot when I hear people talking about AI, it's a new thing and so on. We've been working on embedded devices, making them smart, using algorithms and, classic software, I would say, but bringing intelligence to devices, right? So now everyone wants to do AI at the edge or embedded AI. So it's going to be super interesting to see where things are at when it comes to debugging and working on embedded code. It feels to me like you are a rare animal. There's not so many of us out there. What do you think? Like embedded development is something that I love it. I'm coming from there. I used to develop embedded systems, BSPs, drivers, SDKs, and things like that. It feels like it's hard, and young developers are not so much inclined to go and work in that domain. What do you feel like? Do you feel would you recommend in you?
It's definitely not as popular as it should be, in my opinion. Now, whether it's hard or not, I think it depends if it's properly taught. I think there's way more exposure to classical software engineer, like desktop or web application for young people than embedded.
But we don't need these embedded developers, because to run that intelligence at the edge, as you were mentioning earlier on, you need to have a solid foundation underneath that will run the software on there, and you need it to run properly and be resilient and so on, right? So you need the proper tools as well to do that.
Yeah, the tooling in embedded is always a challenge.
It is always a challenge. Well, there's a diversity of hardware, diversity of compilers, of microcontrollers. It's something that is very close to the hardware, close to the silicon, right? Because you want as little code as possible, because you have little memory, you have little compute power, so you want to optimize everything. So all the layers that web developers and other types of developers are used to, that you can't really, count on when you're doing embedded development.
Yeah, really tied to the hardware. If you work on a ST microcontroller, you need there are a lot of chances that you'll need their hardware abstraction layers and all the drivers. So if you switch microcontroller, then you have to switch all the low-level stack.
Definitely. And so I started embedded development myself 25 years ago. It doesn't make me feel any younger. But I remember a lot of hardware debugging, using JTAGs, using things that probes and things like that would be tied to proprietary hardware from the silicon vendors very often. And these things were very expensive, like very complex, like in French we like to call them usines à gaz, which is like something that is extra complex, extra hard to use, and you need to have like a PhD in each of these tools, something like that. We are in 2025, so 25 years later from I started, and you started like 15 years ago, so you've been at it for a long time as well. Can you tell me a little bit about where things are standing when it comes to debugging embedded systems, testing them, and so forth today?
Yeah. Well, if I continue on what you were saying about JTAGs and proprietary hardware, I think it's better today. You can find more accessible debug probes, and their interfacing with the user are more standardized. There are a couple series of projects out there that let you use them more easily than it was before. But still, working with a JTAG, not only can it be sometimes painful, advanced debug probe will be complex to use, and apart from the difficulty to use it, there's also there are some technical constraint that comes with that might not be adequate for all project. And I will take, for example, something that is a critical application that is, let's say, a plane. You can't debug a plane while it's in flight. You need something else, right?
Whoops.
Yeah.
Eject,
So
eject, eject. Let me test that function.
exactly.
Definitely. No, that makes sense. So you've been working on an open source project for some time. I guess part because you like it and part because of frustration of not finding what you needed out there.
Yeah.
That's a guess. That's not you saying that, but that's a guess. So
Partly
tell
that.
me
Yeah.
about this notion of instrumenting rather than using hardware probes and
Yeah. Okay.
this kind of debugging.
Yeah. So I think there's a when it comes to debugging, oh, by the way, I will be saying here, it's all explained on the website of the project
Okay.
that will show later. So I'll
We, did,
if
we didn't say the
yeah.
name of the project.
Oh
Right.
yeah, it's called Scrutiny Debugger.
There you go.
ScrutinyDebugger.com.
It's going to be in the
If
title and
anything,
so on. But yeah.
yeah, if there's anything that I say that isn't as clear as it should be, go to the website. I've taken a lot of care to explain everything as well as I could. So yeah, when it comes to debugging, I think most people are used to the classical concept of debugging, where you put breakpoints in the code and you try to step into the code. And to do that, you need a debug probe. And basically, that debug probe will hook to the processor or microcontroller through a dedicated hardware channel, right? Like being GTAG or SWD. Um, and it kind of put its tentacle inside of the microcontroller. It accesses the memory bus and looks at what's inside. So that works independently of what firmware runs on the device. There's another approach that we can use, and it's what we're talking today. It's debugging by instrumentation. So rather than putting a probe that comes from the outside, you inject a small piece of instrumentation in your firmware, and then you talk with that, and you get like an insight from within the firmware on what's going on. And this is how Scrutiny work. And there's a couple of advantage to that, and sometimes it's the only way you can really debug something. And I'm bringing back the example of the plane I used earlier.
Yeah. Is that fair to compare that with, I would say, traditional or mobile OSs out there? The way you debug for Android, for iOS, for Windows, for Linux, is using this kind of debuggers, right? You're not using
Well,
a
no,
physical probe, aren't you?
yeah, well, debug more or less, yes. When you debug on an OS, there's way more that happens where you have like all these like the kernel side of the privilege software that will make the communication between different processes. So it's more complex, but you're somewhat close
Okay.
to that.
Yeah.
It does most of it does not apply when you are doing an embedded application without a real OS that has like a kernel basically.
Yeah. Yeah, no, that makes sense. And actually, my point was to lead towards that conversation about the fact that we're still lean, right? So when we talk about these larger OSs, they're bigger because they have all these layers between the application and the resources, hardware, peripherals, and so on, that you have to also eventually debug and go through. But I think it's more akin to, if I were to compare that to more classical tool, to a, let's say, Windows, Windows driver debugger. Like you're like lower level and still
Really?
relying. You're not relying as much on all the OS stacks, all the kernel stacks, in your case. So you're pretty lean. Because you're running on the lean hardware, but we'll see how that works exactly. But I really wanted to make the comparison so that people might understand that we're in between. It's not the full
Kind of.
OS debugger. It's closer to the embedded classical way of doing things, but it's not at the hardware level where you would probe into the hardware to stop the compute and inspect the memories and so on. Still, we'll see that you have a lot of things you can do with the tool that are very useful when you're an embedded developer. And before you get into the demo, I'd like for you to tell me a bit, what are the use cases? What are the best, things
Okay.
that you can do and where you would need a scrutiny debugger?
Yeah. Well, when we started talking, I mentioned that I had a past experience with motor controller, and I think this is a very great use case because debugging a motor controller is hard. It runs at really high speed, tens of kilohertz. Like there is a control loop that runs at high speed. It controls very high current. There's no margin for mistake. A 1 microsecond delay can cause catastrophic overcurrent. So, and as a developer, when you work on that, any almost every problem that you have will translate to the same symptoms, either an overcurrent condition or motor vibration.
Mm-hmm.
So, where do you start when you look at a motor turning at high speed and then suddenly within millisecond it stops and you have a flag, a warning saying overcurrent? Where do you start? Hard.
It's like,
And that happens intermittently.
okay.
So that is a very great use case because what you want to do is monitor all the internal variable at the same time at the speed of the control loop and not miss a single sample.
Mm-hmm.
Um, and for that, you need a dedicated telemetry tool. And I think uh, it's common for my experience, it's common for companies to make their own in-house tool for such type of telemetry. I've seen people doing a configuration tool. Well, they have to write a parameter in a device. They'll make a tool for that. They need to extract some data out of their device. They're going to make a custom tool for that. All of the these different custom tools can all be replaced by a single instrumentation debugger if it's properly done. And
Mm-hmm.
that's what I'm trying to advertise with
Nice,
Scrutiny.
nice. So it's not. So it's way more complex and sophisticated than printfs in your code, right? It's not like you're gonna put
Yeah,
flags
well,
to printf, and the concept might
yeah,
be similar, right?
doing a printf is a form of instrumentation,
Yeah.
but you're limited, very limited. You can do better.
Yeah, true. And then when you do a printf, you output that onto a serial connector or something like that, and all of that is not super fast, not super efficient. And then you go into that motor that is blocked, and you have to read like all the traces all the way back and try and understand what they mean and when they were emitted and so on. So not ideal, but instrumentation, even that's something we used to do. I remember doing embedded development. That was the first thing. Like, did you put some printfs and see what it works, right? But like,
Yeah.
let's see how Scrutiny Debugger works in a nutshell, so that way you get a better idea what's going on there.
Yeah. Well, the concept of like I mentioned, the concept of a runtime of debugging by instrumentation, which is sometimes called a runtime debugger. Uh, it's not something new, not revolutionary, but I think it needs some more attention. The automotive industry uses that, and aerospace also. They have a protocol that are standardized, XAP protocol. They have file format A2L. It's not a new concept. It's just I think outside of these industry, it's not that much use. So okay, so so that is the website, and I'm taking the introduction guide. And we talked about printf, and we see that Scrutiny is an in-between solution between a printf and a high-end G tag, where
Mhm.
you can do more than a printf, but maybe less than a high-end G tag, but it's much easier to use. So the way it works is, if you make a software, let's say this is an embedded software here, where you have a simple variable that you declare.
Mhm.
We see in this example of code that we set a variable to false, and if that is true, then do something. But that will never happen because it's always false. But if you have a piece of software, a piece of code in your firmware that is allowed to modify any piece of memory, then you can make that true from the external world. Right? And that's what Scrutiny will do. You put a little piece of firmware that will accept to do memory dump or write the memory. So it exposes your whole internal memory, and
Mhm.
a software from the external world that knows the memory mapping of the firmware using the debugging symbols can send a command, all right, write the memory address at that location to this value, and then boom, it affects the firmware. And this is what we see here, where there's a little GIF of what it looks like in Scrutiny. We see that the variable that we have in the code translate to, well, they are found by Scrutiny, and you can just edit the values on the fly, and it makes the software. We see that there's a print here, and
Mhm.
it happened in the console from the outside world, even if
Interesting.
this is never set to true.
Interesting. So
Um,
you're going actually way beyond just debugging to find a problem, doing a breakpoint, and so on. You're actually also able to test. You have a set of functions, and you
yes,
want to test them in a certain context. You can say, hey, if I were to have this kind of inputs that I cannot really test in real life yet because I don't have the equipment and whatnot, I can still see if my code will react properly to this kind of configuration that is out there.
exactly. The way I describe Scrutiny, it's a debugging, visualization, and testing tool for embedded C and C++. And
Okay.
we'll see later that you can do tests with the GUI, but it's somewhat limited. But there's also a Python SDK that someone can use to make an automatic test sequence. And you can stub your inputs with the SDK. Imagine you just have to write the memory address that would contain the value of a sensor, and then suddenly you have a virtual sensor that is all emulated with a Python script. So it's very great for hardware in the loop testing.
Nice.
Um, so roughly, in order to use Scrutiny, you have this classical build toolchain. You have some C++ file, you get your O file, pass that through a linker. So what you need to do is to add here this to link with the embedded library.
Mhm.
And now when you get your firmware, you have the debug. You need debug symbols in your firmware. Then you pass that through a Scrutiny toolchain, and this toolchain will do two things mainly. First, it will extract the debug symbol and understand the memory layout of your firmware, and it will also inject a unique hash in your firmware. So we'll use that to identify the firmware and map this to the debug symbol that we just took a snapshot of. So like that, you don't, when you want to debug a firmware, you don't have to have that ELF file at hand. If it's installed in Scrutiny, as soon as you connect your device, your environment loads and it knows the memory layout because it's identified by this unique hash. So now you have out of this toolchain, you have this firmware that has been tagged or injected with a unique ID, and you have this SFD file. This is firmware description file that contains the memory layout and some additional metadata. Those are detailed that are all explained on the website. So you can imagine, you can consider this use case where you have in a company, you have the software team that makes a firmware, and then when it publishes the firmware, it can also produce that firmware description file that contains the memory layout and then gives that to the testing team. And that's all they need to be able to run their test script. Like it contains the mapping of the device. So
Interesting. Yep.
the firmware goes to the customer, the SFD file goes to the testers. Then you have everything you need to do your test.
Interesting. Yeah. Very, very rich. And as you were saying, debugging, testing, I'm curious to see the visualization as well.
Yeah.
That's very promising.
Yeah, so I think we should head directly to the demo of the software at this point, right?
I agree. Let's go.
All right. So here's the UI when you open it the first time. So right now on my desk, I have we don't see it very much.
I think, yeah.
I have this device here. Actually, I have a bunch of them, but this is the one we're going to use for a demo. It's
Okay.
it's an Arduino with an accelerometer. I use Arduino because I had this demo made for a while, but the whole point of debugging by instrumentation is since you put that in your firmware, you're not dependent on your silicon. So I have a demo on Infineon RX, I have a demo on STM32. They're all online. You can go look them up. So yeah, it's just a
Okay.
matter
Yeah.
of compiling the library for your target, and you can get this to work regardless of the vendor. So
Got
we
it.
have this.
Because your linking and your library is very lightweight and
It is
not microcontroller dependent in any shape or form, right? You're very neutral in
exactly.
terms. Yeah, I like that.
And here, that's the proof that it's lightweight. Arduino, they're an 8-bit microcontroller.
Yep. Yep.
It's not,
True. True.
you
Good
can fit
proof.
a
I
lot
like that.
in that.
Yeah.
Okay, so the way it works, Scrutiny is built on a client-server architecture, and that enables a lot of goodies that we'll see later. So when I start, I need a server to work on. The server can be remote. It talks with the client through a TCP socket. So first thing I'll do is I can start a local server just if I want to start to work locally. So I'm going to start my server and connect. Boom. I'm connected now to a server that runs in a different process. Now, what I want is to instruct the server to connect to my device here.
Okay.
So I'm going to connect to my device. You can get Scrutiny to work through any communication channel. So we see
Okay.
here that I have UDP, Serial, J-Link RTT, or even CAN bus. If there's another protocol that needs to be added, it's quite easy to do. The software is designed to be extended in that way, so we could make it work on SPI as far as I'm concerned.
Okay. Is it so? Is like typically, for example, for serial, is the debugger like hijacking one of the serial ports and basically it owns it, and you work against this one, right? So it's
Well,
basically a little bit preemptive on the communication means, right?
it all depends on how you want to integrate it. The library is there, and all it exposes is two streams of data in and out. As an integrator, if you want to put Scrutiny in your firmware, it's your job to move the data from the Scrutiny stream, to a hardware and back and forth. So you can do that in your low priority task. You can multiplex the communication with something else if you want. And which it has a big advantage because you don't have to. If you have a critical task, you can make your debugging process lower priority than your
Mm-hmm.
critical task.
Yeah. Yeah, I was about
And
to ask because, like, when you're debugging embedded systems, sometimes, most of the time, there is a real time aspect or a hard real time aspect, right? You don't want to preempt the actual execution of a task that is higher priority. Otherwise, you're kind of defeating the purpose of debugging because you're intrusive into how things should be working, or you want it to
exactly.
be lower priority, still emitting information, logs, and data, but not preempt the actual real time or higher priority task to run. So you're totally respecting the hard real time structure of the
Yeah.
device, of the system.
Well, it's given to the control of the integrator.
Okay. Yep.
Right. So we're going to use serial, and my device is connected on COM6 here. I'm going to connect, and there's a couple of things that will happen. So we see now my device is connected. So the communication with my device is on. We can see, so this is all the information that the library is giving me. So that's the device ID. That's the unique hash that has been injected in the firmware. That's how you know what firmware you have. So it's a 16-bit device. These are the features that are enabled. You can have memory region that you protect to prevent the access of to prevent Scrutiny from tampering something critical if you want to. So there are two transmission buffer that are assigned, one for reception, one for transmission. So 64 byte, 128 byte. It's lightweight. This is what, as an integrator, I put in my device. I could have used bigger buffer. All it
Okay.
gives you is more a better refresh rate if you would
Yep.
give more memory. Okay, so that is all the configuration of the embedded library. And here we see SFD. That's the Scrutiny Firmware Description file. This is the server that looked at the hash, the unique ID, and said, I know that unique ID. I have that in my database. And it loaded all the memory layout. So that is, the name, that comes from a different presentation. And right. So that is what we know of the firmware. And it has been automatically loaded. Because it has been loaded, we have a variable list here. We know all the variable of the device. Okay? And if I disconnect my device, I'm going to just, excuse me, I'm going to put none here. Then I lose my variables.
Yep.
It's this is the handy part. It's really easy to. As soon as it connects, you have your variables.
Yeah, and that makes me realize you're not just debugging an application; you're debugging the system, right? So the variables you're getting there is whatever is in memory at this time, right? Could be variables that are coming from the serial driver. It could be coming from
Exactly.
something else, right? You're debugging the entire system at once.
Yeah, and we can actually look at that. So I'm going to add a watch window, and I'm going to take all my global variable. I'm going to take everything actually. And let's look at it. So look what we have. Those are the registers. They're moving in real time. Okay, and
Yeah.
the accelerator on the device I have here is called a BNO055. Okay, so I made a driver for that accelerometer, and we can look at the driver work in real time. So it's you see all the internal flag is doing stuff. So now I'm just going to remove some of these variables, because the more variable you have in your window, the more bandwidth it takes, because the server is constantly pulling the device through the serial port.
Yep. And then you're using some of that buffer on the communication input-output that you were describing before. And so the more you put in there, well, the slowest, I would say, it would go.
Exactly. Okay. And you can see it here. Those are the live statistics of the server. It's presently sending, using 60 kilobits of the serial port, doing 40 requests a second. Okay. And if I remove some of those, we can see that the refresh rate of the other variable will start to move faster. And I think, so this is the accelerator value, and I'm going to remove everything below. And we should see the refresh rate start going faster. Well, it was a bit subtle, but it did.
Yeah, it did. It did.
It did. And you see, now we have much more requests per second because I'm reading contiguous memory. I need less requests to fulfill what I'm asking.
Yeah, that makes sense.
Right. So we have the variables exposed in a tree like that. And the tree that we have matches the code structure. So if you have a class, a namespace, each time you go into a nesting, and how you organize your code, it maps to a tree structure like that.
Yep. Yeah. And interestingly, I was talking about printf at the beginning, and you were mapping out functionality, versus complexity and so on. And you could see printf all the way down there. Here we are in concept doing the same thing, right? Because you use serial connection to send the variable value. But instead of having to go and write everything everywhere in your code, printf this value, printf this value, you don't have to instrument the code this way. You're basically instrumenting the firmware so that it will send the data you request through that server and that bidirectional connectivity. Is it described correctly?
Yeah, pretty much.
Okay, awesome.
So now there's a little problem that comes when you do that.
Okay, tell me.
Each time you modify your firmware and you make a new firmware revision, variable, they will move.
Oh, okay. Yeah.
Like if you put a class into a namespace, boom, everything changes, and then the variable is not available anymore at the same location, because every variable has a location, and we see it here. That's the path to the variable.
Yeah.
Now, there's something clever you can do. It's something I called an alias. It's kind of a symbolic link to a variable. It's a virtual variable. So if I go here, I have next to my variable, I have my alias. So I have my IMU here. So I'm going to put that into a different watch window that I'm going to snap here. I'm going to put my IMU here. And now, those are the same value here and here, but
Mhm.
this thing has a different path, and this can be consistent across software revision. And the testing department will be grateful if you do that, because they will want to read a sensor, and if you change your driver, they don't want the variable to move and they don't want to change their test script anymore. They just want to access the sensor. So
Yep.
as a software
Yeah.
developer, you can expose a certain sensor to a defined path each time with an alias like that.
Nice. Nice feature. I
Ah,
like that. Yeah, I can imagine like every single time you change something anywhere in the firmware, your compiler will try and optimize that, even if you're in debug mode. And yeah, I can see how useful that feature can be. It all like the features you're describing, the way you're working with the tool right now, definitely shows that these features have been developed on actual needs and asks. While you were working with it.
well, I would say I'm a power user of runtime of that kind of tool, because
Yeah.
when I work with motor controller, I've tried several software that work in a very similar approach than this, and I've learned the do's and don'ts. And I was a big user. I was making test script for my motors and power converter, and sometimes I would hit a limitation and say, that'd be nice if that would work.
Yeah.
Or I'd like to have a graph with this variable sampling rate. I need to fix this.
Yeah. And I would
So I
assume.
made the tool that I wish I had.
Yeah, and I would assume that as an open source guy, you wish you were able to contribute things to these tools, but we're not, because they were very proprietary and closed. Very often, that's the case because some of these developers, they are developing these tools for the specific hardware. They don't really need or want, or don't have, like, to be fair with them, they don't have the time to optimize for every single thing out there. And
Yeah.
so they are just delivering what they have, and making it closed source is a good way of not having to spend too much time doing things that are not directly related to your actual hardware
Yeah.
business and whatnot, right?
Yeah. And mostly I can do this at my pace. Right.
Yeah.
So sometimes I don't want to work on it. I just take a break. Sometimes I have a burst of motivation and I make a super product
Yeah, I will try and make you
productively.
famous, and you won't have much time because you're going to have all the people trying to use it, and they will file issues and they will propose new features. That's going to be nice, actually. I look forward to that. I'm curious to know. We'll talk about the open source aspect of the project once we've done the demo, but definitely have some questions for you there. Keep,
Okay.
keep going. I'm curious. So you're
Yeah.
visualizing data as a tree view, right? You have other ways of
Yeah.
visualizing,
And
right?
so looking at values like that, it's nice, but you
Yeah.
can't do much. Generally, the first thing you want to do is make a graph out of it.
Yeah.
So I'm going to make a graph here. So that is what I call a continuous graph. So I'm going to put this one
Yeah.
here. I'm going to organize it this way. So let's make a plot of the acceleration. I'm going to put those here, and we're going to call this axis acceleration.
Okay.
And why not put the gyroscope too? Okay, I'm going to put the gyro.
Let's be
Have
fancy.
some
I like the auto
oh,
completion in there.
there.
Good.
All right. Okay. Now let's make a graph. Now
Nice.
I'm moving the device here, or you see it in the. So as I turn it, we see the axis of the accelerator changing.
Yeah. And
I
data
think
is bufferized for the graphs on the server side, right? So the device is just sending. There's no retention of data on the device side of things. Everything is happening on the server.
exactly. No data retention on the device, and actually, we see here that there is two type of graphs. Okay,
Mm-hmm.
the continuous graph is whenever you ask for a variable being in a graph or in the tree here in a watch window, the server start polling for it. And each time it gets a new value, it broadcasts to everyone who wants a value. And the continuous graph is the client, basically my graphical interface, that
Mm-hmm.
is making a graph of that stream of data coming in.
Yeah.
So this has a variable sampling rate because it comes as fast as the server can go. If I start watching new variable, the sampling rate will diminish because
Yeah.
less bandwidth. But you get a feel of what's going on in real time.
You do. You do. Is the data like on the server then usable if you want to go back? Like we were talking about, testing and debugging a problem with a motor, right? And with a motor.
Well, there's something, but not here.
Okay.
This is the client graph, the continuous graph. It's
Okay.
all on the client. The server has no memory of that. It just sends value, and the client decide, okay, I'm going to make a log of that. But I
Okay.
can make it longer. I can stop it. I can save to a CSV or whatever.
Mhm.
I can inspect the graph with a
Okay.
cursor.
Oh, nice.
I
Yeah.
can I'm going to take my two hands here. I can take those. I'm going to hide the gyro, just have the accelerometer. Maybe I'm interested in only that axis here.
I'm
Right?
curious, like, just out of curiosity, what is the graphical library you're using in your project?
The graphical interface is Qt, so that's Qt
Okay.
charts
Okay.
that I customized. So you can,
Nice.
if there's something you want in spec, and we see here that if we start looking at the point, if we look at the time closely, we'll see that the sampling rate is not stable because it depends at whenever this on the scheduler of the OS running the server of the bandwidth available. But so it's good to have a real-time feel, but it doesn't. If you have a problem, say you have an error bit that comes on at some point and you want to catch that,
Yeah.
that's not the right tool because your bit may pass from 0 to 1 between two samples,
Yes.
and you miss what really happened. We have a here. We have a granularity of about, let's see, between two samples, 15 millisecond, give or take, a bit more here. So it's not that fast.
Yeah.
Now, this brings us to the other tool, the embedded graph, and that's useful when you want to do real time. So the way this one works is you're instructing the device to log a certain memory region, and so it's a feature that I call the data logging. So that when you integrate the library in your device, you give a buffer for the data logger. And say I want to look at my accelerometer again. I can do this. Here's my data. I got my graph. Okay, so the device will fill the buffer, its data logging buffer, and when it's full, it's gonna tell the server, "Okay, I'm ready." Then the server reads that, and it says to the client, "I have a new acquisition." And if you look at the sample rate here, it's much more stable. Let's see. Right now, it's more than that. Say that you have a real-time application and you have different interrupt, different task or a scheduler, and you have a task running at 1 kilohertz, so a task running at 10 hertz, so whatever. You can add a probe into each of these tasks, and then you can use those to sample your firmware at that rate. So if you have a very stable, let's say, I'm going to bring back the example of the motor controller. If I have a high-speed task that runs the control algorithm, I'm going to put a probe in there. And if I want to debug the high-speed task, I'm going to make a graph using that high sampling rate. I have a demo that showcased that with an RX microcontroller. It has a 10 kilohertz task, and you can there's some fake signal that you can go and probe, and you can see that depending on your rate, you can get little staircases or smooth values. That is worth checking. But now you just don't want to launch a value. What you want is for debugging, wait for an event. So what I will do is I will take, let's say, let's look at the acceleration. Now, if I'm like that, I have an acceleration of 9.8 in Z. So what I will do is I'm going to log at 100 hertz. I could make it less with decimation. My time will be, idle time, meaning idle time is derived from the sampling rate. Measured time is actually measured by the device. And what I want is a trigger, and it will be whenever my acceleration, and I'm going to move this here. You can drag and drop into the text box. Now, when my acceleration is less than, let's say, 5 G, no, 5 meter per second squared, make an acquisition. And now, and I want to see my event, let's say, at 75% of the graph. We'll see what it means. To acquire. Now, now what we see is the device monitoring the trigger condition, not the client, not the server, the device itself. It does that in real time.
Yeah. Actually,
Whenever
it's the Scrutiny Debugger that is doing that, right? Yeah.
the embedded library of
Yeah.
Scrutiny. So I take my device, and if I pull it down, my acceleration will go down, and I should trigger the graph. There we go.
Nice.
And there we got the event. And look at that. If you make a measurement of the graph, 0% being on the left, 100% being on the right, the event is here at 75%, which is what I asked.
Yeah, so that way you can eventually go back in time in what happened and try and understand the cause of that,
You
right?
can, yeah, you can look before or after the event, depending on your use case.
Wow, yes, like that.
So that's you want to look before if you have a problem you want to debug, but you may want to look after if you, let's say you're looking at the response of a PID
Yeah,
controller.
yeah,
So whenever you get a reference change, you want to see how it's going to stabilize after.
yeah, yeah.
And yeah, so
And
well,
actually, it's this very interesting aspect of it is that instead of being interrupting the process of things rolling, right? You're really narrowing down what you want to look at in terms of data instead of spending hours like trying to get logs, which is hard, right? On devices that have low memory, you cannot log that much down there. You cannot send data at a continuous rate if you don't want to disrupt real time. But here you have an option to go do exactly what you need, which is narrow things down to an event, data a little bit before and after, and you're not interrupting the process with a debugger.
exactly,
Love that.
exactly,
Where were
and yeah,
you 25 years ago when I was doing embedded development? Damn it.
and when you integrate the library in your firmware, you, like I said, there is no allocation done in the library, so you need to define the memory buffer you want to use, and you give a pointer to the library. So the data logging buffer, you can make it as big as you want. So if
Yep.
you have 16K available, you give everything to Scrutiny, and you're just going to have longer graphs.
Yep.
And if you need the memory, then you make it smaller, and your graphs are smarter. Smarter. That's all.
I like that a lot. Pier-Yves, I think I would love to dive even deeper in many things, but I think we'll let people go in there, play
Yeah.
around with the tool. I think it's a good time to. I have a couple of questions before
Yeah.
we sum things up.
Yeah.
Well, we sorted out the real time aspect of things. The tool is not disrupting hard real time when you know what you're doing, right? So something to be careful about, which is prioritizing the tasks that the debugger is going to be running in and things like that. That's done when you configure the library and you compile the firmware, right?
Yeah.
Okay. So that's something that you have to be a decent embedded developer to understand. But the good thing is that this tool is for embedded developers, and hopefully, and you were showing that on an Arduino, will help also people who are less inclined to do embedded development to understand better what's going on down there with tools that are more aligned with the use cases as the one you were describing.
Yeah. It's for the embedded developer, but it's not that hard to use. I mean, you don't have to play with linker script. You just have to add a post build tool chain. And if
Mhm.
you build with CMake, I did all the integration, so it's just a matter of calling one CMake function, and you get your file all ready to go after. Really, it
Yeah,
can be
well,
easy to use.
I like that. So, practical questions. So, you're running that on Windows, both the client and the server today. What kind of
Yeah,
machines can you run them on? Is it only Windows or
no,
Linux? Or
Windows, Linux, Mac, both the server and the GUI, it works.
yeah, okay, awesome, pretty straightforward.
It's
Uh,
actually written in Python, and I compile with the Nuitka compiler that support any platform.
there you go. Awesome, like super straightforward, right? I like that. Another question is, the integration of the tool with IDEs. I like to use VS Code. Is it something on the roadmap? Something you're thinking about? Something already available?
Well, like I said, this CMake integration is all done.
Mhm.
So uh, CMake is platform independent. You can make it work with anything. But you can make it work. The library is easy to compile. It's portable, so you can make it work with any other IDEs. Most silicon vendor have an IDE based off Eclipse, and
Mhm.
they're moving to VS Code actually to with the T really software.
Mhm.
But even in Eclipse, it's easy to make it work. It's not as straightforward as CMake because I didn't do any kind of script to integrate, but I know some people that made it work with STM32 CubeMX.
Okay.
It's Eclipse based.
Yeah. Nice.
I made it work with a couple of other software. Yeah,
Yeah, and there are we mentioned that earlier. There are other solutions out there, right? So
yeah,
and I'm a big fan of saying that there's room for all the products that are out there, all the solutions, all the tools. And so there are some of them that we can, quote unquote, compare Scrutiny Debugger with, so that people can, especially the ones already using these other tools, they might be saying like you were, hey, I would love to have this feature, it's not in there. So what do you want to compare Scrutiny Debugger with, and where would you say it shines the most?
Well, Scrutiny is able to do several things, and there's many software that has an overlap, but I'd like to pretend that Scrutiny is the only one that offers all of the following together. So first, it's open source. It works by instrumentation, so you don't need a debug probe. It has a client-server architecture. Not all software has that.
Mm-hmm.
And as you saw, the discovery of the symbol of the debug symbol is automatic. I connected my device and it loaded. Not all device has that. You need to have the firmware and go find it. On top of that, it has an SDK, a Python SDK. No, not all software has that because they enable debugging, but they're not enabling testing. And so we can think of, for example, Serial Studio.
Mm-hmm.
It's a telemetry tool that works with Serial, but it works only with Serial. It doesn't do auto discovery of data. You don't have a client server architecture, and you need to explicitly define in your firmware what you want to expose. There's a couple of other MCU Viewer is a good software, but you need a debug probe. Doesn't have a client server architecture. It was open source, but it's now closed source. I can think of STM32Cube monitor, closed source. Does need a G tag. NXP Remaster is a very good software too, but it's closed source, and you are legally constrained to use it on an NXP chip. You cannot use it on something else.
Yeah.
So I think really Scrutiny is the only fully open source that has all the feature that I listed.
Yeah, definitely. That's fantastic, Pier-Yves. I think we've given people enough taste of it out there so that they can, go and try it out now. So scrutynydebugger.com. Thanks a lot for coming on the show today. That was awesome. I'd like to discuss old topics. Recently, it's been a lot about, AI at the edge or, cloud solutions. I love that we're coming back to embedded development.
There's several subjects I could discuss about for a while.
Well, so maybe we'll have you back on the IoT show for other topics that are close to the embedded developer's heart, because I know there are a lot out there that are following the show. So go check out the website, the GitHub repo. Pier-Yves, thanks a lot for joining the show today.
Thanks to you, Olivier.